Still can you hear me? So, in today's class, we will discuss the JK flip flop. You might have studied these flip flops. So, I am directly going to this JK flip flop here. So these are used as memory elements, as you know. So, JK flip flop. So, here we have this flip flop as circuit diagram consists of four NAND gates. And there are two inputs first. There are the A and K. Then we have the clock. This output is set to this. Output is set and the this output of this NAND gate I have to break. So here Okay, there is no connection at this point. So, and the third one, so this is the clock pulse, my terminal for J. This is J. And this one is Qn. This is Qn bar. I hope you know these things. This J and K are the inputs. Qn, Qn bar are the outputs. If this is Qn, this is Qn bar. Just like as you studied in SR flip flop. Okay, same scenario. Okay. Now, if you want to know what is the truth table associated with this JK flip flop, so this JK flip flop is another memory element which can store one bit of information with this state Qn, and it consists of 4 NAND gates, as you can see from this figure, and the connections are as shown here. And if you consider the truth table for this particular flip flop, then you have two inputs J and K, and you have output Qn, and then you have Qn plus 1. So previously we do not have any information about this state Qn because we didn't upload any signal yet. So we do not know what is the previous, current state. So this Qn is nothing but present state. It's representing present state, and Qn plus 1 is next state. So we do not know what is the present state. If you consider 0, 0, 0, 1, 1, 0, 1, 1 as your inputs for this JK flip flop, we do not know what is the present state of any of these combinations. Yes, so I can mark it as cross. We do not know what is the present state for this combination. So let's consider 0, 0 first. Okay, 0, 0. If j equal to 0, what will happen in each of those cases? So first I will consider j equal to 0, k equal to 0. Is so you can see from this figure what is the output. So j equal to, now j equal to 1, j equal to, sorry, j equal to 0, k equal to 0. So if this is 0 with NAND gate, as you know, NAND gate is the complement of AND, complement of AND. Okay? So if you consider A, B, C to an AND gate, consider any number of, suppose A, B going to this NAND gate, then you will be getting output as A dot B complement. So if any one of this is 0, A or B, which is 0, which means that if you take the product A dot B, then that will become 0. A dot B will become 0, and take complement of that, that will give you 1. Answer as 1. Okay, so any of this input A, B, if it is 0, then the total product of these inputs, that is, if you take the AND operation of all these inputs, then that will be equal to 0 because one of the input or the variable is 0. So in that case, A dot B will become 0. so that A dot B complement will be equal to 1. Okay, under A or B equal to 0. So if any of the input is 0 for NAND gate, which means that the output will be equal to. So here we are considering clock as 1. So this flip-flop will be working only when the clock is in stage 1. Okay, that you might have studied this in the case of SR latch or SR flip-flop. Okay, not in SR latch. In SR flip-flop, you might have studied this. When clock is 1, then only your flip-flop is active. So we are considering clock is 1 and J equal to 0, K equal to 0. That is the condition. And so J equal to 0, K equal to 0, as you know, the input, one of the input is now for this NAND gates are 0, which means that your output will be equal to 1 for this particular. Here also, the output will become 1 because J equal to 0, K equal to 0. One of the input into the NAND gate is 0, which means that the output is going to become 1 because you have to take the AND operation, then you have to take the complement. So it will become 0 bar, so that is equal to 1. So this output is 1. So this output is going to this particular NAND gate. And if you consider here, this is 1, this terminal is 1 now. And here we do not know what is this value. So it is just Qn bar. Qn bar comes here. Okay. So 1 into Qn bar, complement of that will come as output here. Okay. So Qn will be, what will be Qn? Or I can say Qn plus 1 because Qn is the current state. So I have to calculate what is Qn plus 1. That is next state. Okay. So Qn plus 1 will be equal to Qn bar dot 1 whole bar. So this is the output of the output at this is the output at 1 dot Qn bar whole bar. So this is the output. I hope you understood this because we have one here. Qn bar is coming from this previous state, present state, Qn bar. So from that Qn bar, it is going as an input to this NAND gate. And you have to take the product of this 1 and Qn bar, take the complement of that, that will be the output of this NAND gate. Okay. So that is, this one will be equal to Qn bar will come. So that is Qn. And if you consider, since we do not have any output here as a binary number, 0 or 1, we do not have any high or low values, it's just Qn. So we have to consider the next case also. We have to calculate what is Qn plus 1 bar. This Qn plus 1 bar. So this will be equal to, as you can see, this is 1. And here we have this output Qn, that is present state, that will be given to this input as an input to the next NAND gate, this NAND gate. Okay, so 1 dot Qn will come here. So complement of that. So here it will come 1 dot Qn whole complement. So this will be coming as Qn. So present state is Qn and Qn plus 1 also Qn. Both are same. And we can say that particular state as no change. So in that particular configuration, there is no change in your state because you are getting the present state itself, Qn and Qn bar as Qn plus 1 and Qn plus 1. That is no. So there is no change. Okay. Now if we consider J equal to 0, J equal to 0 and K equal to 1, this is some. So J equal to 0, K equal to 1. What will happen? J equal to 0 means this one again 1, no change. So J is 0. So that one of the input is 0, which means that NAND gate will give output as 1. So this one is, this output is 1. Here it will be 0 because your K is 1. Sorry, this will be. So this one will be 1 and the second one, this is K equal to 1 now. A equal to 1, A equal to 1. So this clock is also 1, so 1 dot 1, no problem. And this output will come here. Output will come here. So that is Qn bar. So here we have Qn bar. Previously also this output will come, but since k equal to 0, because of that, we can directly take the output as 1, because any of the variable or input is equal to 0 means the output of NAND gate will become 1. Okay? So we do not have to consider other inputs. But here k equal to 1, so we have to consider the other inputs whether they are 0 or 1. So we will take first the clock. Clock is 1, so the clock is active. Then we have to consider Qn bar, which is taken from this output to this input of this particular line. So Qn bar 1 dot Qn bar will come as the output. 1 dot Qn bar will come here. So that I will write here 1 dot Qn bar bar. So this is the output of the first NAND. Okay, that is going through as an input to the next NAND gate, this one, along with this Qn. So this Qn will be coming here. Okay. Then we have the product. So 1 dot Qn bar whole bar, that will be given as this will be equal to Qn. So this is equal to, because you have to take the Qn bar. So that will give you Qn. So this side, this terminal is having Qn, this terminal also having Qn. So the output will be Qn bar. Okay. So we'll get Qn plus 1 bar as is equal to Qn dot Qn bar. So you take the dot products here, then it will be Qn itself. That will be Qn bar. Okay, so this is first one. This will be coming. Okay, I have made one mistake here. This connection should come from this connection. I have to take from here. This connection I have to take. This is Qn bar. Okay, so let us in this case, I have made one mistake in this connection. So the last one I have to take Qn bar to this NAND gate and Qn to this. So here I will be getting this one as Qn. So this one will be Qn itself. So that it will come here. So this is qn multiplied with this one. So this will be 1 dot qn all bar, and that will give you qn bar. Now you have to take qn bar dot qn whole bar. So this will be qn bar dot qn whole bar, and that will give my qn plus 1 bar. Here it is qn plus 1. So that is in next stage. So that will give as qn dot qn bar itself. Because when you take double bar here, that will become qn, and you have qn bar. So this is nothing but 1 into 0, something like that. You can consider it as, or you can take this as 0. So if you take qn, you can consider like that also. Then you have to take the complement, then it will become plus. Okay, or will come there. Or you can directly take this qn bar dot qn bar dot qn, this that will give you 0, because if you take multiplication of any quantity with its complement, then that will give you 0. So if you consider a dot a bar, this a dot a bar will be 0, because if a equal to 1, then a bar will be equal to 0, or if a bar is equal to 1, then a equal to 0. So either way, one of this variable will be equal to 0. So if you take the product, then it will become 0. So a dot a is equal to 0. If you take whole bar, then this that will become 0 bar equal to 0. The same scenario here, qn bar dot qn, that is equal to 0. And you have to take a complement of that. So 0 bar will come, and this will be equal. Now if you consider qn plus 1, what is the next stage for qn plus 1? Next phase, that is qn plus 1. So that if you consider that j equal to 0 here, j equal to 0 here, because we are considering this condition, j equal to 0, j equal to 1. So j equal to 0, and this output is qn bar, is coming here. So if it is 0, then you don't have to consider this qn bar, because j equal to 0, then the dot, if you take dot product, that end of quantity will become 0. And if you take the complement of that as an output of this NAND gate, so that will be equal to 1. So here also the output will be equal to 1. And then that one is going through this NAND gate, okay? And the output which is coming from here, it is qn bar. Okay? So 1 dot qn bar whole bar, that is coming as the output of this NAND. So here this is equal to 1 dot qn bar whole bar. So 1 dot qn bar whole bar. So this is the output at qn plus 1. So what will be this output? This output will be Q, because you have to take double complement of this. Then that will be equal to qn itself. Okay. So here we have qn as qn plus 1, and here we have qn plus 1 bar. So here I can say this as qn, and here we have qn plus 1. Qn plus 1 bar is 1, so qn will be equal to 0. This should be equal to 0, because qn plus 1 is, qn plus 1 bar is 1, as you can see from here. And this state you do not know, qn you do not know, but qn plus 1 bar is 1, so qn plus 1 equal to 0, because it is complement. So this one is 0, which means that the reset state is the reset state of your JK flip. Reset state means you are making your output as 0. That is your reset state for JK flip. So that is this condition, j equal to 0, k equal to 0. So this is corresponding to reset state. j equal to 0, k equal to 1. Now let's consider the third one, that is j equal to that. So here j equal to 1, k equal to 0. Equal to 1, k equal to 0. What will happen? Okay, now j equal to 1 and k equal to 0. J equal to 1, k equal to 0. Okay. So in this case, here we have q and bar. So since this part is 0, k equal to 0, this one will be equal to 1 without doubt, because one of the input is 0. Okay, so here it is 1, and this qn will come from this output that is taken from this side. So this will be this is 0. So this 0, this will be 1, or the output of this NAND gate. And here we have qn bar, clock is 1, and j equal to 1. So here we will get 1 dot qn bar whole bar. Qn bar whole. So that will be equal to qn itself, right? This is equal to qn is equal to. So qn, there is qn, then here have here qn bar, right? So qn dot qn bar whole bar will come as qn plus 1. The first one is qn plus 1, that will be equal to qn dot qn bar whole bar. This will be equal to, as we discussed earlier, this kind of scenario, same scenario. So this will be equal to 0 bar equal to 1. Since we already know what is qn plus 1, we can directly write qn plus 1 bar as 0, because it is qn plus 1 is 1 here, so qn plus 1 bar is equal to 0, obviously. And the last one is here. So the last one is j equal to 1, k equal to 1, j equal to 1, k equal to 1. So now what will happen? J equal to 1, k equal to 1. So j equal to 1, we have this output, right? And for k equal to 1, so we have to consider this as 1. So k equal to 1, k equal to 1 means we have to take this qn as a product with this one. So we have to, the output will be this case output will be k equal to 1 here, k also 1. So k equal to 1. So this will be 1 dot, this one is qn whole bar. Here we have same output as the same of that previous case. You can see here, because we already did it for j equal to 1. So j equal to 1, we have this output is qn, and for here we have 1 dot qn bar. This is equal to qn bar, and we have one input coming from this output of this NAND gate. So that is fetched into this NAND gate. So qn dot qn bar whole bar will come. write qn plus 1. First we write qn plus 1. Right? Plus 1 is equal to. So what is qn plus 1? I'm talking about this state. So here we have qn. Here we are having qn bar. So qn dot qn bar 4 bar will come as output. qn dot qn bar 4 bar, that is nothing but 0 bar. And if we consider qn plus 1 bar here, this circuit, as you can see from here, we have qn bar here and qn which is coming from this output. Okay. So here also we have qn dot qn bar 4 bar. Also so this also will give you 0 bar. So here we have qn which is coming from this side. Okay, qn here, and we have here qn side k equal to 1 dot qn, so 1 dot qn bar, that is nothing but qn bar. So 1 dot qn bar will come here, qn bar, and here we have qn, here qn. So in that case, we'll be getting qn. We have to consider. So here we have 1. Okay, since we are having 1 here as your qn, okay, now your qn is 1. So if you take 1 here, then we have qn bar here, qn bar. So that qn bar into 1 will come, and 1 dot qn bar will be coming here. Here also give me this is the so now we have j equal to 1, k also equal to 1. So and clock also 1. ആരെങ്കിലും ഹെഡ്ഫോൺ ഓൺ ഉണ്ടോ ഇപ്പോൾ? So when you consider this is j equal to 1, k equal to 1 state. Here we have one, 0. So this will be giving you qn which is equal to 1. This one I'm saying. Okay. So in that case, this will be equal to 1. This is called as set. It's called as set condition for JK flip-flop. And this is reset. Set means your output is going to become 1. Reset means you are changing your output to 0. And the last state is 1, 1. So for the 1, 1 case, j equal to 1 and k equal to 1. Okay. So in that case, if you consider uh, your values, then first consider this qn bar. So in case of qn bar, we'll be getting this first. We consider this one. So j equal to 1. Here we are having qn bar. And so if you take the dot product, 1 in the qn bar will come. So 1 in the qn bar, you have to take here, whole bar will come. Okay. Now we have qn bar which is coming here also for this second AND gate. So that will give you qn. This is qn bar, whole bar. So that is qn. Here it will come qn bar. So that will give me 1. And you can take that one into this particular side. So if you consider this as, this will be coming as 1 because here you are having 1 here and this one is qn bar. So you take the 1 dot qn, so 1 dot qn bar will come. So qn bar dot qn will come here. Okay. So you will be getting qn here. If you consider this one, we have the result of this one, 1 dot qn bar, okay, so which is coming in this line. So here we have qn bar coming from this output. So if you take doublet complement here, then it will become qn. Qn dot qn bar, that is going to become 0. 0 complement you will be getting at the output of this one. So you will be getting 1 as output for this. And if you consider that one is taken to this one, this AND gate, and then will come 1 dot here this qn bar. Okay, then it will be coming as, here you will be getting qn, which means that you are just toggling your state. You are changing your previous state to the next state. I can explain that with, so we have 1 dot qn bar here, total whole bar. Okay, so 1 dot qn whole bar because qn is coming to this input from here. So that is multiplied with this one, and you'll get 1 dot qn bar whole bar, and that will be equal to qn bar. Will be equal to qn bar, and that qn bar has to be uh, multiplied with this output, that is qn. So that qn in qn bar will come. That will be equal to 0. 0 complement will be your output here. 0 complement, that is equal to 1. So your output here it is 1. So you can say this Qn plus 1 bar, which is equal to, you can say, Qn bar dot Qn full bar, that will be equal to 1. So once it is, this one is 1, and I have to take that one as output to this. Okay. So here I am having 1 now. Here I am having 1. Here I am having 1 dot Qn bar for bar, dot Qn bar for bar. So that will give me Qn itself, because I had to take Qn double bar. So Qn into 1 whole bar will come as output here. So that is Qn bar, Qn bar will come here. So the output will become Qn bar here. So Qn plus 1 is nothing but Qn bar. Which means that if your previous state is Qn, or the present state is Qn, then your next state will be Qn bar. Which means that it is just changing its state, or we can say this kind of phenomena as toggling. Okay, so this is called as toggling in JK flip-flop, because it is changing your state to the next state. If it is Qn is the present state, that will be changed to Qn bar. If it is 1, that is your present state, then that will be changed to 0 in the next next output. Okay, next state. So that is this process is called as toggling. This condition is toggling. This is toggling state. So this we can write here. This is nothing but Qn bar as your output, and that is called as toggling. So this toggling means if you are having Qn as your previous present state, the next state will be Qn bar. So if it is 0 as your present state, then that will become 0 bar, that is equal to 1. Or if it is 1 as your present state, then it will become 1 bar as 0 in the next state. So it is just a total. So if your both your inputs j and k as 1, then your output will be toggled, which means that if your present state is 1, then it will be shifted to 0. Or your present state is 0, then it will be shifted to 1 if both your inputs are 1. So this particular combination, which will give you toggling at the output when j equal to 1 and k equal to 1. So you can just shift your output from low to high or high to low for this condition, j equal to 1, k equal to 1. That is called as toggling. So this is toggling in flip-flop. So let's consider under this condition, toggling, let us consider we have a long time interval, the pulse duration. The clock pulse is having very high duration. Then something different will happen. For example, if you consider the clock pulse, let's say the clock pulse is this. Okay. So when your clock pulse is high, then only your flip flop will be active, and we will get different values for this Qn and Qn bar, that as you know. And for example, if you consider Qn for this particular case is under j equal to 1 and k equal to 1 case, this case. So this is my clock pulse, and if I draw the output Qn, let's say this is my Qn. So initially my Qn is at 0. Initially my Qn is 0 and my clock is also at 0%. So flip flop will not be active at this 0. It will not change its output at when your clock is 0. But when it is going to become high, that is your clock is going to become high, and which means that clock is equal to 1. In that case, flip flop is active, but you are having this j equal to 1, k equal to 1 condition. So this will go to high because my previous state uh, was 0. So because of the toggling condition, j equal to 1 at j equal to 1, k equal to 1, my state will go to the uh, state 1. And then it will remain there. Okay? And when my clock is 0, my output should also come to 0. Sorry, this output will be remaining as it is. Okay? And when it is going to become next state, when my next clock pulse is coming, which means that when the flip flop is active next. So when it is at 0, still it is state is same. The flip flop is inactive, but the output state is same because it is in the same state at 1 as Qn equal to 1. And then it is going to down because of this toggling. Next, when next clock pulse comes, because the present state is at 1, so that it will go to 0 in this state because of toggling action. So 1 to 0, 0 to 1. That is, so this is going like this. The output will be like this at that toggling condition. So this is the effect or the output under this condition, j equal to 1, k equal to 1. So j equal to 1, k equal to 1, we have this toggling case. In this toggling case, your Qn is going to become Qn. Now, there is one problem with this toggling condition. If your clock pulse is having very large period like this, okay. So what is happening in reality? In reality, it will not be like this. So what will happen? Because since you are having your clock pulse, which is very large, as you can see from here, so that the toggling will happen within the clock pulse instead of toggling action happening after each clock pulse. Instead of that, toggling happens within each clock pulse. Why it is happening? Because your clock is already at high position until it reaches at this T1. Well, let's say this T1 and T2. Let's say this is T1 and T2. So within this T1 and T2, it is in the high position. It is clock is equal to 1. Since clock is equal to 1, and you are having this condition j equal to 1, k equal to 1, so that the toggling can happen within this clock pulse. So in that case, what actually happened is we will be having toggling like within this pulse. So in reality, this will happen. So your output is continuously changing. The output is continuously changing. And this side also, we have 0. Here we have 0. Okay. So that which means that present state is 0. So the next when the next clock pulse comes, it is going to high, but it will not stay in high because toggling will happen within the pulse itself because the clock pulse is 1, j equal to 1, k equal to 1 condition is valid. So that the toggling happens within that clock pulse. Okay, like this. So instead of toggling, as we discussed earlier, this kind of behavior will happen in the case of the jacket flip-flop. When you are having your input j equal to 1 and k equal to 1. And this particular process is called as race around condition. Particular process is called as race around condition. So once it is the clock pulse reaches to the maximum 1. Okay. Previously my state was 0, qn, that is the output. Okay, that state was 0. That will go to 1, but it will not stay there. It will toggle. It will come back to 0 again. Again it will go to 1. Again it will come back to 0. Again goes to 1. So within that time pulse that we are having here in between T1 and T2, and within that pulse, clock pulse, we have this toggling effect. And this particular process, which is called as race around condition. And for j equal to 1, k equal to 1, in case of a jk flip-flop, if the clock is too long, then the state of flip-flop keep on toggling, which leads to uncertainty in determining output state. Okay, and you can say if you are considering this kind of state, we cannot say what is the current state because it is always toggling between 0 and 1. So we cannot predict what will be the output in this kind of situation because it is toggling from 0 and 1, from 0 to 1. So that is not a good condition, or it is not a good effect for any memory device because we do not have any certainty in the output which level it will come at. Okay, so this kind of process or condition is called as race around condition, which means that if your pulse is, if your time or the clock pulse is long enough, which means that the period is large, then this toggling will happen within the pulse. Okay, the state of the flip-flop will toggle within this pulse, and the output will become uncertain. And this particular condition is called as race around condition in JK flip-flop. So I am not going to write the definition or explanation of this race around condition. So this is nothing but when you are having JK flip-flop, and if your inputs are at j equal to 1 and k equal to 1 state, okay, and the clock is too long, in that case, the state output or the state of the flip-flop keep on toggling, which leads to uncertainty in determining the output state of the flip-flop. Okay, this process or this condition is called as race around condition in JK flip-flop. In order to solve this particular race around condition, we will use another flip-flop which is called as master-slave flip-flop. Called as master-slave flip-flop. And in this particular case, we will use two JK flip-flops, or you can use JK flip-flop and RS flip-flop also. Since we have the familiarization, we already discussed the JK flip-flop, we can consider the JK flip-flop itself. And we will just show how we can avoid this race around condition in JK flip-flop by using this master slave flip-flop. So we will have this first JK flip-flop as we discussed earlier, and we have this K and K here, and we have this clock pulse here, and this is given to the next. This, and the output of this one And we have the third connection here, the third input. And in this case, we have master slave flip flop. So here we have one more additional JK flip flop. So we have one more additional JK flip flop here. So we need four more NAND gates. And we have output here. So this is the output. And from here, we will take the third input for the first NAND. Okay. So this is how it look like, the master slave flip flop. So we have basically we have two JK flip flops here, as you can see, and we have this clock which is taken from here and which is through a NOT gate, to a NOT gate here. Right. Okay, so here I have this, I have the connection here. Okay, So we have two JK flip-flops here. One will act as master, the other one will act as slave. So we can say this as your master. Okay, this part of this flip-flop will act as master. This JK, this is your master, and the next one is your slave. Next one is the slave. This part will act as slave. So we have basically we have two different JK flip-flops here. So one is acting as master, the other one is acting as slave. So now how we can remove that or we can eliminate that race around condition in this particular master slave flip-flop that we discussed. So let us consider the same scenario with the clock pulse here. And we consider j equal to remember that I didn't discuss any other scenarios with for example j equal to 1 k equal to 0 such kind of examples I didn't discuss here yet. So you can look for that for to draw this diagrams, okay? Time evolution of these pulses, the output and all those things. So we can consider the diagram as for j equal to 1 and k equal to 1 case. So I'm not going to discuss other cases. This is important. That's why I'm discussing this particular case. Other cases you can easily draw, because when you're having clock pulse is high, only that case we are having that state which is going to change. Okay. So correspondingly you can draw all the cases, or in the next class we will do that if it is needed. Okay. So j equal to 1 and k equal to 1, which means that so you are having your j equal to 1 here, k equal to 1 here, and your clock is also 1. Clock is equal to 1 here, for example. So when your clock is 1 here, remember that when your clock is 1 here, this master is active. Master is active, but you have here a not gate. Okay, so if you are given clock as 1 here, here it will become 0. Okay, here it will be 0, so that your slave will be inactive. So when master is active, your slave is inactive. Similarly, if your clock is 0, then this one will become 1. Okay, which means that your master is now inactive because your clock is 0. You are directly given that clock to your master circuit, so that your master is inactive. But because of this NOT gate here, your slave is active. So when your master is active, slave is inactive, and vice versa. So under this condition, when j equal to 1 and k equal to 1, and you are having this kind of a circuit diagram with master and slave, JK flip-flops, if you draw the clock or by using that pulse diagram signals, so we can say the time evolution, we can say this, let's consider this as your clock. We will explain the other output also, and some SR if it is needed, you tell me. You can discuss that. I have started this section directly because I hope you know this SR flip-flop and all those other things from your UG classes itself. So basics of this, the time pulse. So this period should be same. Anyway, so this is your clock pulse. It is varying from 0 to 1, 1 to 0, like that. It is toggling. So if you consider uh, Qn here, if you consider Qn, I will use consider Qn. So how will be the Qn? So Qn is the output. So let us first consider as a master and slave. So we'll consider the output as Qm first. That is the output of the master. So that means Qm is here, Qm, and here Qs. That is the final output. Qs is the final output, which is also the output of the slave. Okay. So I will write it as Qm and Qs. Qs. So Qm, how it will be Qm? As you know, first we are having this clock which is 0. Clock is 0 means the output QM is also 0 because it is inactive now. And then when clock is high, this state is going to become high. Okay. Then it will continue in that state until the next state. Then only the toggling will happen. Then down. Okay. Why the race around condition is not active in this condition? Because when you consider this circuit, you are having Qn here. Okay. Now your Qn is at high. If you consider this clock pulse is high, if you consider this clock pulse is high, let's consider clock is high. And in that case, we'll be having, so this is high now. So in that case, you will be having the output Qn, which is changed from 0 to 1, as you can see from this diagram. The output is changed to this one. Okay. And the output remains in the same state, but it will not go to 0. Why it is not going to 0? Because your total output depends on your QS or QS bar here. Why? Because we have connection from this QS bar to this input, as you can see from this figure. So still, even if your QM is changed because of the clock pulse and the Tongli condition, j equal to 1, k equal to 1, because of that, when your clock is 1, it will change from this present state to the next state. It will toggle. Okay, so from 0 to 1 or 1 to 0, it will happen. So that is possible for master flip flop. So the output of the master flip flop is changed to 1. Okay, but still your output of this entire configuration, that is master slave flip flop, it is still in QS, and QS is not yet changed. So since this output is not going to change, it is fetched into this input, as you can see from here. Okay, it is not going to toggle. It will be as the same as previous, because this slave is inactive now. This slave is inactive, so the output, this is your final output. QS is the final output. So this output is not going to change. Why? Because it is inactive. It is inactive when your clock pulse is 1 here. So as long as your clock pulse is 1, your QS will be inactive. Okay? And QM will not be having any such kind of a toggling effect, because your QM has to get the output from this QS and QS bar. Okay, since there is no change in the output, it will not toggle this time, because even though the clock is 1 here, even though k equal to 1 and k equal to 1, your output is still the same. It is not going to vary until the clock pulse is going to become 0. Okay, so because of that, your output is not going to change, as the slave is now inactive. So that your QM will be staying in the same state. And when the next clock comes, which means that the clock will become 1, it will go to the zero state as the toggling will happen. The toggling will happen in the next clock pulse, and it is going to become 1. And again, it will come. Okay. Now, if you consider QS, QS is 0, and when your clock is high, it will be remaining as 0 because your clock is 0. Now, until it will come to 0, it will be active because we are having this not key. So when your clock is high, that is at this position, okay, your slave is inactive because we are having not gate here, so this will become 0. And when your clock is low, your slave will be active, and it will go to, from this 0, it will toggle to high state 1. Okay, but this time remember that when your clock is at this position, minimum position or 0 position, your master is inactive, so that it will not toggle. Even though your output is going to change, this QS is going to change now. Now your QS is going to change, but still your master output will not change because your master is now inactive, because your clock pulse is corresponding to this master is now 0. So master is inactive. But here it is 1. So slave is active. So the output of slave is going to change from 0 to 1. Okay. But slave also will not be having any toggling effect, because if it is if it wants any toggling effect, then this QM has to change. That toggling has to happen because QM is now constant. QM is not going to change. Time is constant. Time pulse is at its 0 state, which means that because of this NAND gate, NOT gate, this will be active. So it will be just active, and you are having same input as of this QM. That is not going to change because your master is inactive. Since your master is inactive, output of the master remains as same. Okay, so that your output of this uh, slave is also remains as such, QS. Okay. So when in this time your output will be 1, and it will continue in the same. Okay. And when the next 0 clock pulse comes, then this will go down to 0, and again for the next 0 it will come up. Toggling happens, and this will be your final output, QS. That is your final output. So this way we can eliminate the race around condition in JK flip flop by using this master slave flip flop. Okay. So in this case, what we are controlling the output as well as the clock pulse. Okay. Because of that clock pulse, we are controlling the output. So we have basically we have this master and slave. When master is active, slave is inactive, and vice versa. So we'll be having the same output for the master for the clock pulse equal to 1 stage, okay, for the next until the next stage. And similarly for the slave also, we'll be having same input as QM for the slave circuit for the when your clock is at 0 level. Okay, so it will not be going to toggle. So basically this output will be remaining as such, it will not be toggling within the clock pulse, but it will toggle in each of the clock pulse when it is changing from first 0 to 1 and 1 to 0. And so for the master, it is going to toggle in each of these high clock pulse. When clock is equal to 1, it is going to toggle from 1 to 0 and 0 to 1, and like that. And for the slave, it will be toggling when clock is 0. Okay. So this is how we can eliminate the race around condition in JK flip flop by using the master slave. We can continue from here. I will discuss some more details about this master slave flip flop in the next class. And if you need, we can discuss the basics of this SR flip flop also to understand how this working flip flops are working. I think we can stop here. And do this and gate, and from here we have a connection. Okay, so this is the master slave Jacob flip flop, and we have the final connection which is coming from this output to the input. So from here, consider it like this. To this. Okay, so another one from here, and I have to give. Okay, something like this. So this is your master slave JK flip flop, and the first JK flip flop will act as your master, and the second one is acting as your slave. So this portion will be acting as your master. This is your master, and this one is slave. This part is slave. And we also discussed about the operation of this master slave flip flop in the last class. So we have a NOT gate here. This is very important, and this NOT gate will invert the clock pulse. Let's say this is your clock pulse, and this is J. This one is K. Your inputs J and K, and this clock pulse will be inverted by using this particular NOT gate. So when this master is in high state, okay, when the master is having clock pulse equal to 1, the slave will be having clock pulse which is equal to 0 because it is inverted with this NOT gate. Okay, similarly, when the master is having clock pulse which is equal to 0, the slave will be having clock pulse which is equal to 1. So what is the advantage of this? The advantage is that when your master is active, slave will be inactive, and when your slave is active, your master will be inactive. Okay. In other words, when your J equal to 1, K equal to 1 state, if your master is having clock which is equal to 1, so let's first consider J equal to 1, K equal to 1, and let's say let's consider clock with master. Okay, that is equal to 1, and clock master is equal to 0. So at the same state, clock with slave, here it will be 0, and here clock with slave will be 1. So under this condition, so we are considering J equal to 1, K equal to 1, and clock is equal to 1 for master. At that time, slave will be having clock which is 0. And when the clock of this master is 0, then slave will be having clock which is equal to 1. So at this time, what will happen to this output? Let's say this is the output is QM for master. Let's say this is QM, and this is your final output QN. Okay, you can consider it as QM plus 1 also because you are considering the next state. Okay, so let's consider this as your QM plus 1 and you can plus 1. So anyway, so it depends. Let's consider this as Qn itself, no problem. So what will happen to this output when you're considering the output of this master first under this condition, that is clock is equal to 1. Okay. So under this condition, Qm will be equal to, I will erase this play part. First I will show with the master. So this implies what is Qm? J equal to 1, K equal to 1. Okay. And we are calculating what is, let's say Qm is the state of the master, and Qn is the state of the slave. So Qn will be fetched into this part. Okay, this input as input. J equal to 1, K equal to 1, clock is also 1 in this case. So this Qn will be toggled in this particular case. Okay, so we'll get Qn bar here. Okay, but this is not your final output. This is your Qm. This is your Qm. This is not the final output. So Qm, that is the output of the master, that will be equal to Qn bar. That this output will be toggled. Whatever the state which will be toggled. And if you consider the next case, okay, so which means when your master is having clock which is equal to 0, so in that case your master is inactive, so the state will not change. State will not change. And then we will be having the second JK flip flop which is coming. So here we will be getting, when you are considering second flip flop, consider that clock of slave, in this case clock of slave which is equal to 0, and whatever output you are getting here, that is your Qm, which is fed to this particular NAND gate, and this entire system will be acting as another JK flip flop. Now your slave is at 0, so it will not act. It will not change its output. So Qn remains as it is when you are having this master clock which is equal to 1. So at that time your output will be remaining as Qn. And when your master clock is 0, your slave clock will become 1. Clock of slave, that will become 1. And in this time, your output is going to toggle. If you are having a state which is Qn previously, that will be toggled into Qn bar. Okay. So if you consider that diagram, pulse diagram, then so for example, if you consider it like this, you are having this clock. This is your clock. And you are having your output Qn, let's say Qm here, first for master output. So the master output will be toggling. Okay, so initially let's consider the master output is 0, for example. Okay, we initially consider it as 0. So when the clock is 1, when the clock is 1, your master output will be toggling from 0 to 1. So it will be toggling from 0 to 1 state. And it will remain in this state until next clock pulse which is equal to 1 will come. Okay, until that it will be remaining in the same state. So until the next one state of the clock pulse, it will be remaining in this state 1. I'm talking about this Qm, which is this one. So this Qm. So the master will be at 1 until the next clock pulse. When it comes, when the next clock pulse comes, which means when the clock pulse will become 1 next time. So in that time, it will toggle to 0. It will come back to 0, and then it will continue in this state, 0 state, until the next one, next one state of the clock pulse. So this, when this one comes, it will toggle again to 1, and it will continue in that one until the next uh, one position, or the high position, or the high value of the clock pulse. Okay, then it will go to 0 and continues. So this is the output corresponding to QM, that is for master. Now if you consider for QN, that is the final output of your master slave JK flip flop. So QN will be, uh, as you see from the figure, when your clock is maximum or clock is high, your slave will be inactive. Okay, because we are having this NOT gate here. So the time clock pulse will be having 0 at this particular moment towards that slave, when you're having clock pulse which is equal to 1. So for a slave, it will be 0. So for the entire output Qn, if you consider, then we have to consider it like this. So this will be starting from 0. We are considering it is also starting from 0 initially. Then it should start when your clock pulse is minimum, because we are having a NOT gate which is connected to this slave configuration. So it will be getting that clock pulse equal to 1 when your original clock pulse is equal to 0. So up to that point, this Qn remains in this state, which is 0 initially. And then when it is reaching at this clock pulse state, that is 0, okay, that will be inverted by using this NOT gate, and your slave will become active at that moment. And then this 0 state will be toggled into maximum. And it will continue in that state, in that one state, until the next 0 of the clock pulse, until next 0 of your clock pulse. So this next 0 is coming here. So until that, it will be continuing in its high position. So it will be continuing at that point, and it will be coming down, that is toggling to 0. It is coming down to 0, and it will continue in 0 state until the next 0 of your clock pulse. So this will be continuing 0, and then it will go to high state and continue in the state 1 until the next 0 of your clock pulse. So it will be like this. So this is the pulse diagram for this outputs QM and QN for the case of master slave JK flip flop. So here you can see that we do not have any kind of trace around condition. We just have this toggling. We have only this toggling. One more important thing is that with this connection, as we know that as we stated earlier, when you are having this state equal to 1, then only your JK flip flop will be toggling. Okay, but in this case, that is not the condition. This toggling will happen at the negative triggering. Okay, at the negative triggering. So we can see that, or we can say that this negative edge of your clock pulse you can consider. So in each of this negative edge of the clock pulse, okay, as you can see, you are getting the output which is toggled. Okay, so for each of these negative edges of your time pulse, so if you consider this as your time pulse, this is your positive edge, this is your negative edge. Okay, so when you are considering the master slave JK flip flop, at this negative edge of your clock pulse, it is changing its state, or it is toggling. So we can say that the master slave flip flop toggling at this negative edge of your clock pulse. Okay, so this is called as negative triggering or inverted triggering. So at that point we are having this toggling in the master slave JK flip flop. Okay, so we can also say that this is an inverted triggered circuit, or it is a negative triggered circuit, or flip flop. This master slave JK flip flop, because the toggling happens in this negative edge of your clock pulse. Okay, so by using this JK master slave JK flip flop, we can avoid the race around condition, and we will get only this kind of uh, toggling as your output. When you are having j equal to 1 and k equal to 1, we will be having this kind of output, which is just toggling the state from 0 to 1 or 1 to 0 continuously. So that we require in case of counters as an application. So that is the basics of the master slave JK flip flop. And one more thing that you have to, I hope you understood this operation. So when you are having this, the NOT gate connected here, okay, so we are actually controlling the master and slave operation with this NOT gate. Okay, so in only one of this circuit or one of this section of this master slave flip flop will be active within that clock pulse one time. Okay, within if you consider one cycle, only one of this will be active. Or if you consider one state of this clock pulse, I cannot say cycle, one state if you consider, then only one of this will be active. So with that we can avoid the race around condition, because for example, if you consider when the master is active, okay, when the master is active, you will be having your output change up to here. Okay, that will not affect your total output because slave is inactive. Okay, slave is not operational now, so you will be having the same output as such. So your output will not change because your slave is inactive. So it will be remaining in your previous output itself. So no race around condition will happen. Yeah, even if you consider next time the slave will be active, but the master will be inactive, so that you are when you are considering this output which is fetched back into this input, so this will not be working. Okay, because your master is inactive now. Okay, so you are having here, we are having same input, j is j and k are same, and we are having this NOT gate which is fetched to here. So the output which is given by the master is same, that is not going to change. Okay, so then we will be having same qn as your output for the entire state of the clock pulse. So this is how the master and slave work, and we will not be having any trace around condition if you are using this master slave JK flip flop. So we eliminated the race around condition, and we successfully achieved the toggling. Okay, without having any kind of race around condition. Now there is another flip flop which is called as D flip flop. This you might have studied in your UG classes. D here, D stands for data. Okay, so we know basically the SR flip flop. I hope you know this basics that I didn't covered here. So let's consider SR first, and Qn plus 1, that is next state. So if your clock is 0, then this will not work. Okay, you will be having same state because nothing will change. So previous state is Qn, next state is Qn plus 1, that we already discussed in the previous class. So Qn is the previous state, so Qn will be remaining as it is when you are having clock pulse which is 0. When your clock is 1, then only the circuit starts its operation, and the values will change. So if it is 0 0, then it will again change. There is no change will happen in SR flip flop. if you go back and check what is the operation of this SR flip flop, okay. And when your clock pulse is 1 and S is 0 and R is 1, we'll be having reset condition because R is 1, R stands for reset, is for set. When R is 1, you are having reset, which means that your output will be having value which is equal to 0. Reset means 0. And when your clock is 1 and your S is 1 and R is 0, then we will be having set condition, that is your output will be assumed to be having value equal to 1, or output will change to value 1. And then clock is equal to 1, both this S and R 1, okay, and this is an invalid condition for SR flip flop. This is an invalid condition. Both of the inputs will not be, should not be equal to 1. So this is invalid and this will not use. We will not use this kind of configuration in SR flip flop. Okay. Now, when you are considering this SR flip flop, this is the basic truth table of this SR flip flop. You can go back and check how this is working SR flip flop. I'm not going to discuss those things here because this you have studied in your UG class itself. Okay, so this is if you consider this SR flip flop, as you can see from here, we are having this as your previous state, which means that they are remaining as such your previous state. So this will be acting as your some sort of memory because it is remaining as it is in that particular state. So it will be acting as a memory. And if you consider this states 0 and 1, okay, that we will be going to use to change your state. Okay, whether you want to change from your state 0 to 1 or 1 to 0, we need only these two conditions. Only these two we need. And here also we can see that we are taking the complements. Okay, if you are taking S equal to 0, then R equal to 1. Or if you are taking S equal to 1, then you are taking R equal to 0. So we are just taking the two inputs, they are inverted. Okay. So considering these two states, okay, they will be acting as your memory. So we are not having any change in your output if you are using these conditions. Okay. Under this condition, we do not have any change in your output. If you want to get any change in your output, then we have to use this particular case. So correspondingly, we have S and R values, which is 0, 1, and 1, 0, which means that when your value of S is equal to 1, your R will be equal to 0, and vice versa. So we are just complementing the inputs. We are having two inputs, S and R, but we are just complementing the inputs in such a way that we are having some change in state. So instead of using two different inputs, why we cannot use a NOT gate which will perform the same operation? So that is the question asked those times, and that results in this D flip flop. So if you consider this SR flip flop, okay, so we can draw that here by using this block. Consider this as your SR flip flop. So this is your input S, this is the input R, and we will be having output Qn as well as Qn bar here. Okay, so these are the output. And for input, we are having S as well as R. Two inputs are there. Okay, so we are not considering these two states. We are not considering these two operations because that will not change your state, output state. And this we will not consider anyway because this is an invalid condition. Both of these inputs should not be equal to 1 in case of SR flip flop. That will not give you the right result because your Qn should be complement with the Qn bar. When you are applying this condition 1 and 1, then this 2 is going to be equal. Okay, so that is not a valid logic reason. So that this condition is not used in anywhere. So it is an invalid condition. Okay. So we'll use only this force, this four, but among these four, we are having only these two set for your state changing. If you want to change your state, then you have to use this. In such case, we do not require, actually, we do not require two inputs. Instead of that, we need only one inputs, and we just have to make the complement of that input and fetch to the next input. So what I mean by that is, if you are considering this as your S, so I am considering this as the only input I am having, okay? And from this input, I am connecting a NOT gate, and that is connected to this R. Now we will be having same condition. If, for example, if you consider that S equal to 0, let's consider that S equal to 0, what will happen? If your S equal to 0, R is going to 1. R is automatically, it will change to 1. Okay. And when your S equal to 1, your R is going to become 0. So these two conditions, this particular operation can be achieved by using a single input and a NOT gate. We do not require two inputs. That has to be given separately. So now if you consider this whole setup, if you consider this whole setup into a single box like this, okay, then it will be looking like this. We are having this one. We have two outputs. So this is Qn, this is Qn bar, and you have only one input. So all these other circuits will be going inside this block, and this input is your D. And this particular flip-flop is called as D flip-flop. Okay. So now you can see from this particular case, we can simplify that SR flip-flop with two inputs to a single input flip-flop to get this particular condition. Okay. And if you want to write the truth table for this D flip-flop, how it will be? We consider the clock pulse. Oh, clock pulse also will be there. For this, we are having clock pulse. So that also you can consider. Okay. So I didn't consider here the clock pulse, but the clock pulse also will be there. So you can just connect that here. That is your clock pulse. Okay, so if you consider the truth table, how it will be? If you are having clock pulse here, let's consider clock is 0. Clock is 0 means this flip-flop is not active. So you don't have to consider what is the value of D. Anyway, you will be having your Qn plus 1 state will be Qn itself, because it is just the previous state. When your clock is 0, flip-flop is not active. So whatever state is there, it will be remaining as such. Okay, so Qn plus 1, that is next state will be the previous state itself. And you do not have to consider this. So this is a don't care condition, D. Whatever the value of D, it is not a matter, because if the flip-flop is not active, then whatever the input, it is not a, if you consider any circuit or any machine, if it is not on, it does not matter whatever input you are providing to the machine, because it is off. So similarly here also, if your clock is 0, then your flip-flop is inactive. So it does not depend on the input. Okay? So it is a don't care. You don't have to consider this input in this particular case, and you will be having the same state Qn as the uh, next state. And when your clock pulse is 1, now your flip flop is active. Then it is also depending on your inputs. So if your D is equal to 0, what will happen? If your D equal to 0, consider this. Uh, consider this two. Okay, so when D equal to 0 and D equal to 1, two states are there. Clock is 1, D equal to 0, D equal to 1. These two are possibilities. When D equal to 0, your S is equal to 0. Here you can see. Let's consider this as your D, and this will be equal to 0. D equal to 0 means your S is equal to 0. S is equal to 0 means set. Condition is set. Set means your output is going to become 0. When your D equal to 1, D equal to 1 means S equal to 1. Okay. Sorry, in this case it will be reset. So reset it will be equal to 0. Okay. For D equal to 1, your S is 1. So it is going to become set state. And in that case, it will become, this output will become 1. Set means 1. So this will be 1. Reset means 1. Sorry, reset means 0. So I will repeat that. So when your D equal to 0, which means that your S is equal to 0 here, and this side we have NOT gate, so your R is equal to 1, which means that reset is on, or reset is equal to 1. So when reset is 1, which means that your circuit is resetting your previous state. So your entire stored value, that is Qn, that is going to become 0. Resetting means it will assign the output, or the Qn value as 0 when your R equal to 1. That is corresponding to reset condition. So when your D equal to 0, S is equal to 0. When S equal to 0, and this is complemented here with this NOT gate. So R is equal to 1, which is reset. Reset means your output will become 0. When your D equal to 1, when your D equal to 1, just opposite of this will happen. So when D equal to 1, this is going to become 1. Your S equal to 1, S equal to 1 means set state. Set means your output is setting to 1. So it will become 1. So this will be the truth table for D flip flop. And this is very important. This we will be using in the next registers and all the other applications. Okay. So this is how the D flip flop works. Okay, and we have another. This is I have explained all this by using the SR flip flop. Okay. Similarly, we can also use JK flip flop along with this. JK also we are having same similar condition 0 1 1 0 condition we have, and there also we can convert that JK flip flop into D flip flop by the same scenario. Okay, so we can have it like in that case we'll be having JK flip flop. So I'm not going to discuss how we can convert that in case of JK. I'm just drawing how it will be in the after conversion or those things. So let's consider this as your D, and that is your only one single input given to this circuit. So this will be J and K now, your inputs, and this D will be noted and given to this K, and there here also we'll be having two outputs, Qn and Qn bar. You can go back and check what is the working of this JK flip flop. We already discussed that. So in this way also we can have that same kind of scenario, whatever we have discussed in case of SR flip flop. Here we have to consider the negative triggering. Okay, so we have a dot here. When you are applying this clock pulse, we have a dot here, which means that the JK flip flop is now active or toggling in that negative edge, okay, of your clock pulse. So this is a negative triggered circuit or flip flop. Okay, so this will be a D flip flop by using JK. This is similar to this one, okay, as you can see. That you can also check with that truth table. It will be having same output, but the difference comes here with that negative triggering of your JK flip flop. Okay, so that's all about introduction to this D flip flop and JK flip flop. And if you want to know much more about these basics, then we have to you can look into the basics of your degree classes, where we have that SR latch, SR flip flop, and the output of those SR flip flops. And then D flip flop also some beginning is there. So all those things that you can learn from that uh, lower classes. Okay. So if you're having any doubt, you can ask now. Otherwise, we can go to the next section. I'm still in. ഇതിൽ എന്തെങ്കിലും ഡൗട്ട് ഉണ്ടെങ്കിൽ ചോദിക്കുക, അല്ലെങ്കിൽ അടുത്ത സെക്ഷനിൽ പോവാം.
സർ നെഗറ്റീവ് ട്രിഗറിംഗ് ഒന്നും കൂടെ ഒന്ന് പറയോ?
നെഗറ്റീവ് ട്രിഗറിംഗിന്റെ എന്താ പറയണ്ടേ? നെഗറ്റീവ് ട്രിഗർ ക്ലോക്ക് പൾസിന്റെ ഇവിടെ വരുന്നു. When you are considering JK flip flop, okay, the JK flip flop will be having the toggling when it is at this state, when your clock pulse is equal to 1 or when your clock pulse is equal to 0. So your JK flip flop, if you consider JK, in that case we discussed that the toggling will happen or the flip flop will be active when you're having this state, when your clock pulse is equal to 1. So that's what we have here. QM is changing from 0 to 1 when you are having the pulse, that is the time pulse. This is your clock pulse. When your clock pulse is having value which is equal to 1, so at that time only it is going to change its output from 0 to 1. So this is the toggling action from 0 to 1, and it will be remaining in the same state, which is 1, until the next one appears for the clock pulse. So this is next one state for the clock pulse. Okay, so when the next one comes, it is going to toggle again, but this time it will be toggling from 1 to 0. It is toggling from 1 to 0. So it is changing to the state from 1 to 0. Then it will be continuing in that 0 state until the next one comes for the clock pulse. Okay, this is the next one state. I'm talking about this state. Okay, so when it starts, when this one comes, that is the clock pulse, when it is going to become next maximum, then it again toggle from 0 to 1. So it is going from 0 to 1 and remaining in this state, and this process continues. And this is for JK flip flops. So QM is the output of your master. So the master is nothing but a JK flip flop. If you consider this output, okay, I will write it here. So if you consider QM is this output, so this is nothing but a JK flip flop, right? So the JK flip flop will be having output which is just like this, as we drawn here. But when you consider the output of the master slave JK flip flop, as you can see from here, that is QN. That is the total output, this one. That is the output of the master slave flip flop. So if you consider Qn, then in that case, it is going to toggle when you are having the pulse which is going to zero, which is going to zero state, which is not toggling when it is going to the one state. So when it is going to zero, the total output of this master slave flip flop or output of the master slave flip flop, which is toggling from zero to one. Okay, which means that the toggling happens when the clock pulse is going to zero. That's why it is called as negative triggering or negative or inverted triggering. Okay, so initially we consider that when the clock pulse is going from zero to one or the one state, which is correspondingly the state is going to change for the JK flip flop. But here, just reverse of that, when the clock pulse is going to become zero, the toggling happens. Okay, so this is why it is called as negative triggering. So here it is just opposite of check flip flop is happening. When you are having this zero, it is going to zero. It is triggering, sorry, toggling from zero to one, and it is remaining as such, which is equal to one, and then it is coming back or toggling again when it is when it is the clock pulse reaches the next zero. Okay, when the clock pulse is going to next is zero. So at that moment only it is toggling again to from one to zero. So this particular condition is called as negative trigger, which means that we are just taking inversion of that clock pulse. Okay, so if you are applying that clock pulse like this into your flip flop, okay, which means that your flip flop is active with clock pulse which is equal to 1. So this is CLK equal to 1. Under this condition, this flip flop will be active. So if your flip flop is active at this condition, which means that your clock is 0. So clock is 0, you are taking note of that. So you will be getting 1 at the flip flop. So this note is nothing but a NOT gate. So if you are applying this NOT gate, so your clock will be 0. Okay, clock is 0. Clock is 0 applied to this NOT gate, so it will become 1. And this clock is 0. That's why it is called as negative trigger. Okay, that's why you are using this symbol for that particular case.